I'm pleased to introduce the speakers for this first session, and we'll start with Professor Bruce McCandliss. Bruce is the Piggott Family Graduate School of Education professor at Stanford University, and he's the founder and director of the Stanford Educational Neuroscience Initiative, which seeks to forge deeper connections between advances in neuroscience, insights into learner differences, and innovations in educational interventions. He received his PhD in cognitive psychology with certification in cognitive neuroscience from the University of Oregon under the mentorship of Michael Posner, and completed his postdoc training at the Center for Neural Basis of Cognition at the University of Pittsburgh and Carnegie Mellon University. His work at the interface of neuroscience, cognitive science, and education was honored with national awards, including the Transforming Education Through the Science of Learning Award and the Presidential Early Career Award for Scientists and Engineers. He's also a founder of the Synapse Brain School Brainwave Learning Center and an investigator in the nationwide Adolescent Brain and Cognitive Development Study. Let's welcome Bruce. Thank you.
Anybody in the audience who's a parent, or anybody in the audience who imagines that they're going to become a parent, is struck with this profoundly moving kind of inspirational idea that human development in the period from early childhood to early adolescence is a time of remarkable transformation within the human brain as well as within the human mind. When this period, this very vulnerable period of human development, is supported by high quality education, new cognitive fluencies emerge, which become foundational to the intellectual mind for the rest of your life. New cognitive fluencies emerge through the support of these transformational educational experiences that we have in school. Parents spend tremendous amount of time considering what school will their child go to? What's the nature of this school? How well is their child doing in school? How are they engaging in school? How is their engagement with school transforming who they are and what they can do with their mind and brain? When it goes well, these new cognitive fluencies allow you to do remarkable things. Just by studying how 26 visual symbols might combine to form thousands and thousands of words, you can engage in amazing journeys of intellectual engagement and stories and imagination and new concepts and new theories. By mastering certain concepts within mathematics, you can find new ways of navigating the physical world as well as the imagined world. We know from decades of functional brain development studies that these cognitive transformations that are happening in the context of schools are also marked by changes that occur within the brain. We can study functional changes within the human brain as they're being supported by these schooling experiences. So what I would like to do just in the next 25 minutes is give you a brief introduction to some really exciting work that's happening inside the Stanford community, which is actually connecting these two worlds of scholars that are at the leading edge of understanding what are the dynamic forces within education. What are the ways in which teacher practices may engage young minds and lead to these cognitive transformations, as well as some really exciting work that's happening within the world of neuroscience within Stanford. And since this is the 10th anniversary of the Symposium, I wanted to take a minute to just call out how the Stanford neuroscience community and the institutes have actually made bold strategic investments in these far-reaching visions of what neuroscience can be and how it can contribute to society. So one way in which they did this was through some really exciting seed grants. Several $100,000 allow some scientists to get together with some postdocs to start studying really fun, interesting questions. So for instance, in a skilled adult mind who went to school and has immersed themselves in symbolic thought, you can do some remarkable things. You can look at a display and then think about the magnitudes of these numbers and these contexts, and then you can engage in a little bit of cognition to decide whether you're going to imagine placing this line in the left visual field or the right visual field. You can do this imagining number space transformations. Jay McClelland, Tony Norcia, and I set about some functional imaging to discover how different parietal circuits in the brain, in the expert, are coordinating both these number magnitude computations as well as these spatial computations, and discovering that there's distinct roles that anterior and posterior regions of the interparietal sulcus play when coordinating these two things in your mind when you're transforming number magnitudes into spatial actions. Another seed grant supported some really interesting work that's been kind of pioneered by Tony Norcia of steady-state visual evoked potentials that can help us map out electrophysiological changes in the brain that occur not just with really rapid visual stimulation in the sensory system, but also psychological discriminations of numerosity that can be embedded in a steady state stream at exactly one cycle per second. Tony's group has found that using reliable components analysis can pull out topographies that are exquisitely tuned to exactly this frequency in the brain and help us map out the electrophysiological response to these psychological discriminations of numerosity. We can start to study how they become increasingly tuned in development, and it becomes a remarkable tool for studying these things, and I'll come back to that. Another way in which the Stanford Neuroscience Institutes have supported this transition is through a very generous interdisciplinary training program that brings together people with expertise in developmental cognitive neuroscience, neuroscience training, together with people with expertise in education. This program, which was actually started right when I arrived at Stanford, was able to gather millions of dollars of support, of external support, in order to carry out this cutting-edge interdisciplinary research, bringing together people from the neuroscience community, from postdoctoral scholars who already had training in developmental cognitive neuroscience that wanted to learn more about how this can be connected with education, together with students that are studying within the Graduate School of Education in the Developmental and Psychological Sciences program, linking different ways of using neuroscience to gain insights and make connections with education. The timing of this coincided with a very, very bold and remarkable study of developmental cognitive neuroscience banding together 21 different labs to study 12,000 youths as they developed in their brain from 3rd to 8th grade. This was happening at a time when there was lots of concerns about potential impacts of substance abuse on neurocognitive development in these children, but remarkably, even though they were studying the development from 3rd to 8th grade, there was also almost no educational assessment linked to school achievement, school environment, or these abilities. So this provided an opportunity for the Stanford Educational Neuroscience Initiative to sort of jump in and take on a crosswalk between databases that are happening at Stanford, 50 million educational tests from 3rd through 8th grade every single year, every school, every child in the entire nation, in which we can see how differences in educational environments, educational capital, access to educational opportunities is having profound impacts on these cognitive fluencies of mathematics and literacy. We, in a sense, have a nation of very, very entrenched inequities that are translating into the cognitive fluencies of each generation in mathematics as well as in English language arts. We were able to carry out a crosswalk between these using the school identification data, so that now in the ABCD study, we have very, very specific information for every single participant in the study of which exact school did they go to during their entire journey through school, what were the qualities of the school, what access did they have resources, as well as how these schools were doing at supporting these basic cognitive fluencies of mathematics and English language arts. This crosswalk allows new kinds of questions to be addressed that haven't been addressed before. So for instance, in collaboration with Jason Yateman's lab, one of the Sensei trainees, Ethan Roy, has been studying white matter tracts, specifically left arcuate fasciculus, and linking these overdevelopment directly to qualities of the educational environment that the students are in. 2 years of white matter tract development within the left arcuate fasciculus is related to the specific environmental qualities of the school, which can be separated from the qualities of the neighborhood. We think that school is having a significant impact on human brain development during this very vulnerable period between early childhood and early adolescence. We can kind of zoom in and see this. This is brand new work that I think Jason Yateman just submitted. Hopefully the reviewers are kind. It also opened up opportunities for us to do chronometric analysis of these cognitive fluencies at a very, very fine level. So being an investigator within the ABCD grant, I was able to champion and harass and lobby the neurocognitive groups to put into the study just 6 minutes of chronometric testing, which can allow us to look at the changes in the cognitive fluencies associated with mathematics so that we can run chronometric studies that compare different cognitive loads within sort of non-symbolic processing, arithmetic, as well as more complex arithmetic forms. And we can see how these cognitive loads are changing over the course of development from 5th through 8th grade and beyond. And we can link this specifically to changes that are occurring in different educational environments. Interesting story. When we first did this, it was a very regimented lab-based study in which an RA was sitting with a child with exact 50 centimeter distance between the screen and the study. Then COVID hit, and we were only able to collect about 1,200 kids. We were stuck, so the Sensei team was able to pivot and to turn all of these cognitive assessments into completely remote assessments that could run on 15 different models of smartphones and tablets. They could just be downloaded and run in the home. And luckily, this sort of analysis of chronometric engagement of a kid's cognitive fluencies is incredibly robust to all of these differences. And maybe all of the fussiness that we had about our laboratory assessments were maybe a little bit over-engineered. Now, having cognitive fluencies in mathematics for every single child, or most of the sample we could access within ABCD, opens up new possibilities for neuroscience to ask new questions. We can start to ask, what is the relationship between resting state connectivity in different brain networks and a kid's emerging fluencies in mathematics? There's a core at Minnesota run by Damien Fair, which breaks the connectomics of the ABCD study into different arms that are very well matched for demographics and allows them to explore resting state connectivity relationships to brain sort of behavioral assays in one arm and then test it a priori in another arm and vice versa. And one of the kind of exciting discoveries about this is that across all of these different ways of testing and generalizing, it seems that the frontal-parietal network of resting state connectivity in a third grader is the best network in the brain to predict the fluencies of a fifth grader. And we can study these longitudinal relationships across this. This is early work that's not yet been subjected to peer review, but it gives you a hint of the new kinds of questions that can be asked when expertise in education and cognition are combined with opportunities within neuroscience. And I just want to close with one of my favorite things that I've done since coming to Stanford, which is to actually start collaborations with real schools and become very, very invested in the complexities in situ of what's happening inside of a living K-8 school. We've been able to use outside support and some seed grants started from neuroscience institutes to embed a state-of-the-art electrophysiology lab within a kindergarten through 8th grade innovative school in Menlo Park called the Synapse School. This allows us to study complex changes in development that are happening from kindergarten all the way through 8th grade to study individual differences, and also to study the relationship, perhaps even causal relationship, between how certain teaching practices of engaging children in new learning can lead to changes in brain activity. Crucial to this is the structure of this collaboration is embedding 2 PhDs in educational neuroscience as directors within the school. And this allows them to collaborate with teachers and find opportunities to teach kids about neuroscience, engage teachers in thinking about different brain systems, cognitive fluencies, and many other things, and allows us to tackle these big goals of exploring how brain activity is transformed through learning experiences within their very school, explore ways of thinking about how insights into our brainwaves can enrich our educational experiences, as well as, ideally, this is the part that I'm sort of most passionate about. Is it possible that we could inspire a sense of awe and wonder about how our brains are changing with learning right in the very essence of the kindergarten through 8th grade transformation that's happening before our eyes and invested in by our parent communities? This, having a brainwave lab on site, is not only pedagogical, but allows us to engage in cutting-edge peer-reviewed research. Some of our early discoveries, I showed you back at the early part of the talk how Tony Norsh's work has found these powerful ways of combining steady-state visual evoked potentials with reliable components analysis to tune into brain activity related to psychological discriminations that children are learning, like the difference between a word that they know and a made-up word, which has sort of equal properties in terms of combining letters into a word form, leads to a brain response that we can quantify even in kindergarten children. And we can see how it develops over time. But we can also study a very different sort of psychological discrimination. Children are starting to infer statistical relationships between letter forms as they form visual word forms, which forms the basis of their engagement with text. And this produces a rather distinct topographic response or reliable components, and we can quantify how these 2 types of psychological discriminations are developing live within schools. One remarkable discovery that came from this is that specifically children's insights into how letters are combined to form words, these statistical relationships between letters combined into word forms, is changing pretty dramatically from kindergarten proficiency all the way up to 2nd grade proficiency. Another great affordance of collaborating with a school is that you can invite the children back. So as children returned from COVID, we were able to take a large cohort of these children to see how their reading development had changed over time, as well as how different brain signals were changing, different psychological discriminations they were making in their brain, and we were able to find very powerful relationships at the individual level between the amplitude of sensitivity to these orthographic psychological discriminations and increases in their fluency with naming letters rapidly and with reading. The other great affordance, and the one that we're just starting to embark in, is the ability to engage with the school in benign natural experiments. We can actually collaborate with teachers to teach children different things or teach them in different ways. And then we've created a sort of a operating procedure in which teachers agree to engage in a 2-week learning sprint in which they try to encourage cognitive advances with very specific materials that we can counterbalance across multiple teachers. And we can start to surround that with pre-post brainwave learning center sessions of EEG in order to see how is it that a manipulation that we introduce here, either by materials or teaching style or different ways of engaging children in learning, may lead to a change in brain activity. And we have some exciting results already that are under peer review that I'll be sharing with you in the future. But I also want to point out that we're not restricted to this very sort of reductionistic use of just elementary forms of stimuli in your brain's ability to integrate it to do other things. We can take very naturalistic stimuli. We can have a child relax for 20 minutes and engage in a narrative story, and by lining up 20, 30, 60 children exactly at the same time point, we can start to study inter-subject correlation patterns that emerge. And new projects are starting to collaborate with schools to ask, could we engage 7th and 8th grade teachers to teach children how to engage in a story, how to engage in a particular genre of science fiction or theory of mind evoking romantic narratives that might help them to change the way they engage in a narrative while they're listening? And could we use pre-post imaging of this sort in order to map out these changes? The last thing that I wanted to point out is really, really remarkable opportunities when a community, a remarkable community such as what's happening in the Stanford neuroscience community, can actually start to collaborate and engage with school communities. I didn't really plan this, but the directors of the school created a middle school research assistant program in which aspiring 6th, 7th, and 8th graders could say that they want to learn about brainwaves even more. They want to participate in a lab. They want to even join committees that can make decisions about what questions should we answer next and how can we answer them. And this program is now in its second year. The first cohort of students were able to not only learn the techniques that we typically teach first-year graduate students within the Sensi program, they were able to master them and then learn enough to be able to propose their own questions, and then take the results of those questions and apply to science fairs at the regional, the state, and even national level. And remarkably, one child, or a youth I should say, who was struggling with issues of dyslexia and having profound and challenging discussions about how his dyslexia was impacting his sense of self, his sense of worth, his imagined futures. This youth joined our program in the middle school research assistant program and carried out a series of studies comparing children that had dyslexic tendencies versus children that did not, and finding really interesting differences across them. This poster went on to be presented at the International Congress for Developmental Cognitive Neuroscience, also known as Flux, and was given the Poster of the Year award, to which his family was very celebrating. But even more than just winning an award in our achievement-focused culture, I got this letter from the parent that really opened my eyes to what's possible when you think about this notion of inspiring awe and wonder at the possibilities of thinking about neuroscience and the potential development of children and their futures that I want to share with you. With permission, I redacted the name. For my son, having time to explore the dyslexic mind and contribute to new research has completely altered the way he thinks about his own abilities. Being a BLC, that's the Brainwave Learning Center, middle school research assistant, this is the first cohort of this kind that we created, has been an essential part of his emotional and academic growth over the last 2 years. It's mind-blowing that a middle school student could receive such close mentorship from neuroscientists. We couldn't be more grateful. I never anticipated that something like this could happen when communities of neuroscientists collaborate with parents and teachers about what might be one of the most important issues of our day, which is how is it that we support children during this very vulnerable part of human development? So I'll stop there and maybe have time for a question. Maybe Jay wants to ask me about parietal lobe.
I don't know if you knew, Bruce, that I was dyslexic as a child.
I did. I didn't want to volunteer that, but okay. Now that you've outed yourself in public, we can all sympathize.
I can't say I have a question for you, but I can say that I'm deeply inspired by what you've shared with us, and by the journey we've shared together. I don't know, other people don't know that I was the director of the Center for the Neural Basis of Cognition in Pittsburgh, and we did studies on experience and behavior, not so much the brain at that time, together in Pittsburgh. So I just wanted to express my profound appreciation for what you're doing and how you've been able to bring this work, into contact with things happening in people who started out like I did when I was in the 3rd and 4th grade. Those were tough years for me, just like for this kid, I'm sure. And so appreciate what you're doing.
Well, right back at you, Jay. Your contributions have been inspirational for me and have actually enabled me to imagine these future worlds, that one of which I find myself in now. So deep appreciation for you and what you've contributed.
Very exciting research. Are you finding results that will have implications on home learning if we ever have to go to a shutdown of schools again?
Yes, that's a really, really interesting issue. And I don't know that any of our results have profound implications for home learning. However, there is a tremendous opportunity within the ABCD study. There has been never a cohort of 12,000 students that have been more quantified in the very years before the pandemic struck. And although the pandemic was incredibly disruptive for studying this cohort, nearly all of them are back. And we've been able to issue surveys to them, asking them, how do you feel about school? What is your disruption looking like? What is the relationship with your parent in navigating this school? And we've made some discoveries that typically parent involvement and parent reports about involvement and student reports about parent involvement have very little relationship to how a child reports feeling about school. However, that changed during the disruption. It turns out that during the disruption, parental involvement has a tremendous impact on how children feel about school. And we've been able to get insights into very specific forms of parental involvement, such as the parent engaging the child intellectually in the material that they're working on seems to have a tremendous impact on how the child reports feeling about school in general. However, remarkably, the more mechanical and pragmatic parent involvement has very little impact on their kind of emotional response or their emotional report from schooling. We're going to be able to have an unprecedented insight into the very specific nature in which schooling during this age was disrupted and the impact that it has on these neurocognitive abilities that we can measure using chronometric analysis and brain analyses to be able to study this. This requires a very bold integration of radically different data sets about school disruption. You can imagine how complex that data set is and the multiple stakeholders that are sort of in charge of quantifying in all these myriad different ways. But in that data, if it can be successfully crosswalked with the ABCD data and the CETA data, can give us new insights into this remarkable cohort that has had its disruption right in the middle of their education like no other. And many people are quantifying this from different ways, but I think the ABCD is going to give us very, very powerful insights into how this is impacting brain development, how this is impacting the sort of connectomics and neural dynamics that are happening within an individual that might relate to their schooling, their education, and their future intellectual development. Potentially. Yeah. Yeah, great question. Thank you.
I'm afraid we're out of time for questions for this talk. Let's leave Bruce a round of applause.